Hello students, my name is Shashank Shekhar and today is the 8th lecture of the alcohols, phenols and ether chapter. Today we will start basically with the ether. Okay, so we'll see the nomenclature of ether and preparation. So if you look at the syllabus here, so we have covered so far this alcohol and phenols whole. Although we have not seen the uses of alcohols and phenols, we will see this in the last class. But we have covered all the chemical preparations of this, say, alcohols and phenols and their physical and chemical properties. Okay, also we have seen their nomenclature. Right now we'll start this ether, which is kind of different from this alcohols and phenols, as it has a OC bond, CO bond, and two CO bonds. So basically alcohols and phenols have one CO bond. This ether have two CO bonds. We will look at the structure to see what is the difference between the structure of the alcohol, phenols and ether. Okay, so if you look at the topics that are to be covered today, first we will start with the nomenclature of ether. So nomenclature of ether is a bit different to understand. I will not say difficult, it is different to understand because different logic is applied there. Okay, next, the illustration of naming. So we'll see also illustration of how we can name certain ethers. After that we will see the structure of ether. I am including this structure of ether because it is important to see why these ethers are least reactive. So in the next lecture we will see the reactivity of this ether, and you will see there that these ethers are less reactive as comparison to any other functional group we have seen so far. Then we will move to preparation of ether. So in every chapter, whether haloalkane, haloarene, phenols or alcohol, we have seen preparation of each of those. Similarly, we will see the preparation of ethers. Although this it has not much wide varieties of this preparation methods for ethers, but there are some. We will look at those. First is the dehydration of alcohol. We will look at the mechanism also. There is an exception to it. We will look at that also. Clear? After that, we will move to the famous synthesis. This is Williams synthesis. So I would suggest that this is more important in this lecture. So this is the most important thing I would suggest. Okay. Then we will see an exception of this Williams synthesis. Clear? So let us start our today's lecture. First of all, the nomenclature of ether. So what is ether? So if you look at here, you will see that ether is basically are two alkyl groups, either to compound containing two alkyl groups which are bonded to the same oxygen atom. So it is written here also that ethers are compound having two alkyl or two aryl. Yeah, aryl group can be also present. That would be called as aromatic ether, which is bonded to an oxygen atom. So you can see the general formula here. Here R1 and R2 can be alkyl or aryl both. It can be any aliphatic chain. Now, the ether functional group does not have a characteristic IUPAC nomenclature suffix. Okay, so what does it mean? So it means that if you have seen in the previous classes, you must have seen that this alcohol and all of these have a suffix. Okay, they have a suffix, like we have ethanol, right? We have ethanol, and then we have oic acid for your carboxylic acid. Then we have Al for your aldehyde. We have on for ketone. But for your ether, we do not have any such constraints. Okay, so we have a thing called alkoxy group. So do not interpret it as ether. Okay, this just means this group. So this group is called as alkoxy. So you must have seen ethoxy, methoxy. So if some, say, alkyl group is attached to a oxygen through single bond, then that group will be called as your alkoxy group. So if methane is attached, we will call it as methoxy. If isopropyl is attached, we will call it as isopropoxy. If phenol is attached, we will call it as phenoxy. So what is isopropyl here? So I am making this thing clear. This is isopropyl basically. Okay, so this is the group. So similarly, this is phenoxy, which would look like this. That is phenol, a derivative of phenol. Whose one H atom has been removed. Okay, so this is phenoxy, isopropoxy and methoxy. And this is their name and this is their structure. If we look at this alkyl group from which it is derived, it is methyl, it is isopropyl for isopropoxy, and it is phenyl for phenoxy. Clear? Now, ethers can be named by naming each of the two group as a separate word. So we have seen that we have two groups here, this one and this one. Now, oxygen will go with one of the group. We will see it, with which it would go. But the idea is here is that we will, after giving oxygen to one of the alkyl group, we will have two groups primarily, and both of this group will be named separately. Then there will be space in between them. After that, we'll write ether word after that. Okay. So suppose first group is, suppose our oxygen goes with R2. Okay. Then we will write the name of this group, then the name of this group, followed by the word ether. We'll look at illustration to get a more clear idea. Now, the OR group, which with the alkyl group with which the oxygen goes, is named as alkoxy. Different alkoxys we have mentioned here. And the smaller, shorter alkyl group. So what do you mean by this? It means that oxygen goes with that alkyl group that has a greater chain length. The one with a shorter chain length is the one with the shorter chain length. The oxygen atom goes with that carbon atom which has a shorter chain length. Sorry for the confusion. So I want to say that the oxygen group goes to that group, oxygen atom goes to that group which is shorter in length, and it is named as alkoxy substituent, while the longer alkyl group side becomes the alkane base name. So suppose we have a methane, okay, attached to this CH3. So this will be called as methoxymethane. Clear? Now suppose we have the group like this. We have a group like this, C2H5. Then I have said it that the smaller group takes the oxygen. Then its name will be methoxy. Then which is the longer chain, it is C2H5, which means it is just your ethane, that is, it is your ethane whose one H has been removed. So it will be methoxy ethane, that is the base name for our ethane, along with the word ether. Methoxy ethane ether. Clear? We will see to it. Each alkyl group on each side of the atom is numbered separately. So this is the most important thing, that in most of the, say, functional group, we have seen that our numbering is for the parent chain only, but for your ether we have two chains. Okay, so on both sides of oxygen we have two chains, so we have to number each of them separately so that each of the groups can be named separately, right? The numbering priority is given to that carbon closest to the oxygen. So it says that we will number in such a way that the oxygen, that the carbon to which oxygen is attached should get the greatest priority. Next, the alkoxide side has an oxy ending. The same thing written here, this oxy ending. Okay, so now let us look at a illustration here. So this is the structure that we are looking upon. Now how we'll name it? First of all, we will identify the longest carbon chain. So which is the longest carbon chain? So on this side of oxygen we have only one methyl, but on left sides of oxygen we have this group. So let me mark it with a different pen. Okay, so this is the thing. This is one of the group, and the other group is this. Sorry, yeah, other group is this one. So which one is the longest one? The left one is the longest one. Okay, left one is the longest one. So who will get the oxygen? I said earlier the shorter one will get the oxygen. Therefore it is written as methoxy. Okay, just follow it one by one. Now, at which position the methoxy is present? At which position the methoxy is present? It is present at first position. Okay, so this one is written wrong. Sorry, it will be methoxy. Yeah, this group will be called as methoxy. Or you can think of it this like also. Okay. So it is why it is written 2-methoxy, because the longest chain is this one, and we have a methoxy group on the second part. So what I mean here is that, so since we have got this chain as the longer one, we'll start numbering it. This will be 1, this will be 2, this will be 3. Okay. Now at the second position, we have methoxy and your methyl group. Which are the two groups? That are methoxy and the methyl group. So how I will name it? So here is it written that a methoxy group is attached to the second carbon of the atom, and a methyl group is also attached to the second carbon of the parent chain. So how we will name it? We have two substituents on the second carbon, methoxy and methyl. So we will name it 2-methoxy 2-methyl propane. Why it is written propane? Because this is 3 carbon. So this is your IUPAC name and this is your common name. Sorry for the confusion. So this one is your common name, tert-butyl methyl ether. This is your IUPAC name. Okay. Now you would ask that why we have written this methoxy first and this methyl afterwards. Why not we place this methyl first and methoxy afterward this methyl? So for this, you should follow the alphabetic order. What we should follow? We should follow the alphabetic order. So you can see here that this methoxy has a greater priority if we follow the alphabetic order. METH is common in both of this. METH, both have METH, but after that we have O here. But for methyl, we have Y here. You know that O comes first in the alphabet. Therefore, we have placed our methoxy first, then our methyl. So 2-methoxy, 2-methyl. After that, our propane group is here. So we have written 2-methoxy, 2-methyl propane. Clear? So in this way, we have named it through the rules of IUPAC. Now, one thing I have told you in the start, and that should be noticed here also, that we do not have a different name for ethers. Like we have different suffix for ether. Okay, so you can see that we do not have any we do not have any suffix here. This oxy group is not for ether, it is basically for this group. Clear? So it is 2-methoxy 2-methyl propane. Now let us look for this common name. Okay, common name. So how I will name the common name? So for that, we have two substituents on both sides. So we will give the common name to each of them. So this one is called as tert-butyl group. This is called as tert-butyl group. So we have written tert-butyl first, and then we have a methyl group. So tert-butyl, methyl ether. Now we will ask that why we have written tert-butyl first. The reason is obvious. We have followed the alphabetic order here also. Therefore, it is termed as tert-butyl methyl ether. So in this way, we can name our ether. Clear? So this is the IUPAC nomenclature of ether. Now I would suggest you to see more and more examples in such way, because naming of ether is quite different from all of the functional group, and it may create confusion that what would be the structure of the given name. So you should be keen about this thing. Now the next thing is the structure of ether. What it is? The structure of ether. So basically I have told you in the start that I am teaching you this structure of ether to get a clear picture why this ether is not reactive. We will see how it is not reactive. We will see the reactivity of this ether. But for now, just assume that okay, this is least reactive of all the functional group that we will study in this class 12. Okay. Now, if you look at the structure, then ether is composed of a central oxygen atom, which is here, and which is bonded to two alkyl groups. Now, if this thing is symmetric, that is your ether is symmetric, then it would have a bond angle of 111, that is 111.7 degrees. But this bond angle is not consistent with our tetrahedral geometry, because according to tetrahedral geometry, it should be 109.9 degrees 7 minutes, but it is not so. Why is it so? Why is it happening? Because we have lone pair, and lone pair has more repulsion as compared to the bonded pairs. Therefore, due to greater repulsion between this lone pair and the bond pair, we got a lesser bond angle. So this is just to decrease the energy. So if we place this in the configuration same as tetrahedral, then lone pair and lone pair would come closer, and also the lone pair and bond pair. That would result in greater repulsion, and repulsion always tend to increase the energy of the system. Clear? So this is the thing. Now in ether, the oxygen atom has two sigma bonds. It is very obvious. It has two sigma bonds. with 2 carbon atom attached to the alkyl group. Same thing written. So these bonds are formed by the overlap of sp3 hybrid orbital of oxygen with the sp3 hybrid orbital of carbon. What it is written here is that you can see that this oxygen is, although this is not a perfect tetrahedral, it is a sp3 hybridized atom. Similarly, this carbon is also sp3 hybridized. Therefore, we have a bond between the sp3 of this and sp3 of this. So there is basically a sigma interaction, head-on-head overlap between the sp3 hybridized orbital of the oxygen and carbon in this case, and similarly in this case. Here also the bond angle is 141 picometer. So talking about this parameter, that is bond angle and bond length, these are specific to this structure only, that is our this symmetric methane ether, but it is not applicable to all of those, and you will not have to worry about that also. So I am just giving an illustration. Clear? Now each sigma bond is formed by the head overlap. The same thing written. The lone pair on the electron on the oxygen atom occupies one of the sp3, leaving the 2 sp3 orbital available for sigma bond. So it is written that since we have overlapped one of the sp3 orbital, so in sp3 how many hybridized orbital will be present? So sp3 has 4. 3 comes from p orbital and 1 comes from s orbital. So we have total of 4. So 2 are involved in bonding and 2 are involved to keep the lone pair. Okay. So this is the overall structure. This is not written right. Okay, this is wrongly written. Okay, so let me cut it out. Yeah. Now, what is the most important thing? The most important thing is the reactivity. So generally, we have seen that the functional group has greater reactivity than the normal alkane group. Ether is also the same properties, but compared to other functional group, it is very less. Why is it so? Because both sides we have carbon. Both sides of the oxygen we have carbon. Therefore, electronegativity experienced by this bonded pair and this bonded pair are kind of same. They are kind of symmetrically distributed, near to symmetrical, because it may have much more chain, it may have less chain. All of these criticalities can happen, but the next adjacent carbon is same on both sides. So we have carbons on both sides. Therefore, the polarity of this bond and this bond is quite low. Okay, what does this affect? So it affects directly the reactivity. So you must have seen in all the reaction we have a negative charge, or a negative delta negative charge, which is kind of nucleophile which attacks on electrophile. So for the development of charge, or for the attack of charge also, we must have a center that should hold a small amount of charge, about delta positive or delta negative or -1 and +1. But due to the less polarity, it would result in a small charge development on either of this atom, that is carbon and oxygen. Okay, so due to this thing, we have kind of less reactivity. You can also look at the nomenclature for a practice here. So it is termed as methoxymethane. Why is it so? You must figure it out by yourself. It is a simple structure. Okay. Now, this was about the structure of ether. Now let us move to an important part, that is preparation of ether. What chemical methods we will use to prepare this ethers. So basically 3 methods are here. That is dehydration of alcohol, Williams synthesis, and from alcohols. So we can have another method for preparation of ether, in which you will use alcohol only, but that would be different from dehydration. So we will look this method tomorrow. Today we will see this dehydration and Williamson only. So if you have time, we will cover this also. Clear? So let us start from dehydration of alcohol. So again, we are here with the dehydration word. So dehydration means removing of hydrogen. What it is? It is removal of hydrogen. Okay. So you must have seen this reaction. Okay. You must have seen this reaction. So alcohol undergoes dehydration in the presence of protic acid. So this is very important. What is protic acid? First of all, protic acid means the acid which contain H+ ion. So there are acids which do not contain H+. So those are called as non-Arrhenius acids. So we have our AlCl3, which is Lewis acid. Basically, it accepts electron. So since you have moved to higher class 11, 12, so you cannot just stuck to the primitive idea of acid and base, that H plus donor is your acid and your OH minus donor is your base. So that is a primitive definition. Now you should move to a much higher definition, that is your Lewis acid and Lewis base. You should look at each of the aspect. I would say that your Arrhenius concept of H plus and OH minus, your Lewis acid concept of electron donor and electron acceptor, your Bronsted aspect also. So you must look at each of these to get a more clear idea of what an acid and base is. Okay, so there are acids which are aprotic in nature, which is AlCl3. So for your dehydration of alcohol, we should need this protic acid. So if you look at the application of this Lewis acid, you must have seen this kind of reaction in which we use FeCl3. That is Friedel-Crafts alkylation that requires our this Lewis acid, right? Okay, that is a different story to tell that we will see later. Coming back to our reaction here, so the formation of reaction product alkene or ether, it depends on reaction condition. Okay, so if you look at the reaction condition of both of these reactions, so if you see, we have the same reagent, we have the same substrate, only the reaction condition, that is temperature, has been changed, and you can see the drastic change in the functional group. So the first one, which has a higher temperature, it gives your ethene, that is the removal of H2O takes place here. But at a lower temperature compared to this, that is 413 Kelvin, we got a ether. So this thing should be noticed. If you want to think about it, you can think it in this way, that since we are supplying a higher temperature and water evaporates at higher temperature, it is just a mnemonic device to remember things. Okay, it is not the mechanistic way to remember things. You cannot give the logic that it is happening in this way because of the higher temperature. I am just giving you a mnemonic device that if you see a higher temperature, then you should try to remember, okay, since it is a higher temperature, water boils at higher temperature, therefore it will form alkene. So removal of water will take place and we will get alkene. It is just a mnemonic device to remember things. So I used to remember things in this way only. Clear? So it is written here also. For example, ethane is dehydrated to ethene in the presence of sulfuric acid at 443 Kelvin. But at 413 Kelvin, ethoxyethane is the major product. So this is ethoxyethane. So again, you can see that what is the importance of remembering the nomenclature. So while you read a book, any standard book, and suppose you are reading your rearrangements of book like SN Sanyal or your NCERT also, then you will see that if you remember this nomenclature, then you will be able to grasp this book more efficiently. Because if you do not know the IUPAC nomenclature, you have to go back to the rules and see it again, that okay, this is the thing, this is the thing. Then it will be difficult for you to correlate. Okay, so for that reason, you should be very specific about the nomenclature. And in most of the standard book, this IUPAC nomenclature is followed. In case you see a common name nomenclature, then you can refer to it. That is a different thing. But in most of the cases, they follow the IUPAC nomenclature, and it becomes easier for you to understand things. Okay, is this clear? Yeah. So where are we? We are in the reaction thing. So if we apply a higher temperature, then you will get a ethene, or simply you can say alkene. If it's apply a lower temperature, then you get your ether. That is your required product. So since you are interested in your preparation of ether, so we will look at this mechanism. Look at its mechanism. So what is the mechanism of this reaction? So here is the mechanism that we have. So the first thing about this reaction is that it follows a SN2 mechanism. So those who are thinking about it, what is SN2, or those who are forget, let me make a quick line to it. That SN2 mechanism basically involves one-step reaction, means a direct attack takes place and the bond formation and bond dissociation takes place at the same time, whereas our SN1 involves the formation of a carbocation. Now let us get back to our reaction. So do not misunderstand me that okay, you have said that it happens in one step, it is happening in 3 steps. It is not the way. I am just talking about the nucleophilic substitution that is occurring, that is this step. So if it was SN1, then it would have been occurring in 2 steps, but since it is SN2, so we are seeing a single step reaction. Clear? Okay, now let us start our reaction. So first of all, we have our ether, we have our alcohol, right? So we have used the acidic condition, we were using H2SO4, so it will protonate our alcohol. So we'll get this kind of protonated alcohol that is having positive charge on oxygen. Now next, what will happen? We have another mole of alcohol. So how we are saying it another mole? So it is very clear. If you take, I will not say another mole, I would say molecule, since we are seeing one by one. So this is molecule. You can tell it mole also, but for mechanistic part, you should go with your molecule. One mole cannot attack. We cannot think of such a high population at one in one shot. You must consider only one molecule. Okay, the idea is that it does not mean that this mechanism does not involve mole. You can think it of a mole also, but that would be very you can say that would be very confidential confidence step, because you cannot think that okay, one mole would attack on one mole at one at a time. Therefore we'll think it as one molecule. Okay, now whatever. So first we have protonated your alcohol, then we got this thing. In the next step, another molecule of alcohol will come which has a lone pair on oxygen. It will attack our carbon. Now why it is attacking our carbon and not on oxygen? Why is it so? So the thing is very clear, that your oxygen atom is already fulfilled. It has a positive charge. Okay, it does not have a space to say attack or facilitate the attack. Or you can imagine it in this way also. It is basically the difference between the HOMO and LUMO. So what is this HOMO? So we'll not get deeper into it. I'm just giving you a short definition. So HOMO is basically the orbital that is occupied and has the highest energy. So we have different orbitals in a molecule, that is molecular orbital diagram. You must have seen molecular orbital diagram. So different molecules have different orbitals, and each of these orbitals are filled. So the one which is the highest energy, that is filled also and has the highest energy, that is called as HOMO. And that is being used by the oxygen atom to donate electrons, because the energy goes from that to another one. Now we have LUMO, the lowest unoccupied molecular orbital, which is just the orbital that is above your HOMO. This is your HOMO, this is your LUMO. Now since this is carbon and it is oxygen, and you know that electronegativity of oxygen is higher. So if something has a greater electronegativity, then its energy comes down due to attraction between your nucleus and electron. So your HOMO comes down. Clear? So your HOMO comes down. Now since it has to donate electron in a higher shell, okay, it has to donate electron in a higher shell, then it would prefer carbon. Okay. Also, if you see that here, so if you want a simple answer to it, you can also think that suppose it would have attacked here. Clear? So it does not have an empty orbital to accept that electron. Okay, it does not have an empty orbital to accept that electron. Or you can say it does not have an anti-bonding to accept that electron. And also it is a good leaving group. So once it attacks here, this H2O is a good leaving group. And this H2O leaves, and we are left with this thing. Now oxygen has since one more bond, therefore we have a positive charge on oxygen. Clear? And the H2O is kicked out. Now how it is SN2? Because this attack of your you can say formation of this bond between oxygen and carbon, and the breaking of bond between carbon and this oxygen, they both are occurring at a same time. Therefore it is a kind of concerted mechanism, and hence it is SN2 mechanism. Next, since this reaction was acid catalyzed, you must need your H plus back. So in the last step, your H plus is taken back to oxygen, and we are left with your ether that we were looking for. Now I would say that there is one more method that is more appropriate, because if you see say H plus, that it is present in H plus form. So acid is not present in this form, it is always present in H3O plus form. So if you try, you should try with the same with this H3O plus. Just the H plus donor will be H3O plus species rather than the bare proton. Try to do this. At last you will get your H3O plus back. So this is a kind of homework for you. If you want to take reference, you may see the dehydration of alcohol. There we have taken the H3O plus rather than H plus. Now the method is suitable for the preparation of ether having primary alkyl group only. Why is it so? Because the alkyl group would be less hindered. So we know that SN2 is kind of attacked from backside. And if it is more hindered, suppose your secondary carbocation, then would be hindrance from the second carbon. So that attack would not be facilitated. So for that reason, that would result in alkene rather than your nucleophilic attack. Clear? So it is written also the alkyl group should be unhindered and the temperature should be low. Both should be clear. So if it is not hindered, if it is hindered, then it would result in an alkene. Also, if you have higher temperature, or you cannot say you would say that if it has not optimum temperature, then it would result in an alkene. Clear? So I'm saying, what I'm saying here is that alkene is a more say suitable product for this reaction, that is dehydration of alcohol. But since we are interested in ether, so we would try to keep the condition in such way so that we can get our ether. But the backward, or you can say drawback, sorry, the drawback with this method is that it's not appropriate for primary greater than primary ether. So you cannot use it to prepare an ether which is not primary. Clear? Next is Williams synthesis. So since we cannot do it with the dehydration of alcohol, we use the Williams synthesis that can be used to prepare tertiary ether. But in this case also, you cannot have tertiary on both sides of oxygen. You can have it on one side. So for that, why is it so? For that, you have to look at the mechanism. So it is a very important laboratory method that is used for the preparation of both symmetrical and unsymmetrical ether. Okay, so this is one more point. So if you see the dehydration of alcohol, then you must have seen that the product there was a symmetrical ether, while in Williams synthesis you can form the both symmetrical and unsymmetrical one. So what do we do in this reaction? We take alkyl halide and a, say, your deprotonated alcohol, okay, or you can say alkoxide. We are taking a sodium alkoxide. So we react it with your alkyl halide to get this thing plus NaX. Now ether containing substituent alkyl group, that is secondary, may not be used for this method. So it is saying that ether containing substituted alkyl group. So we will see to it why it is so. We will see the mechanism. So in this reaction, the reaction involves SN2 attack of an alkoxide on primary alkyl halide. So the alkyl halide should be primary. It cannot be secondary or tertiary. Your alkoxide can be your, say, secondary, primary, tertiary. We have no problem with it. But your alkyl halide must be primary. Otherwise, it would give elimination reaction, or you can say acid-base reaction, more clear, more suitable word for it. So we'll see the mechanism for that. So this is the thing. So better results are obtained if the alkyl halide is primary. So if the alkyl halide is primary, then only the better results are obtained. In case of secondary and tertiary alkyl halide, elimination competes over substitution. So since we have used a stronger base, so stronger base and a weak nucleophile. Why a weak nucleophile? Not a weak nucleophile, I would say. Not a good condition for a SN2 attack, because we have seen that it is a SN2 attack, and if we use our primary alcohol, sorry, tertiary or secondary alcohol, then it would defacilitate our attack of the alkoxide ion, and it would be easier to remove a proton rather than to substitute a halide. Therefore, in that case, alkene will form. For example, if we take the reaction of CH3ONA with CH3CBr, sorry for this, it is wrongly written. Okay, so how it will happen? So what are the reactants? So it is CH3O minus Na plus CH3 and Br. So this O minus will take an H from this carbon. This bond will go here and this Br will be removed. Okay, so we will get CH3OH plus, so we got this H from here, plus one alkene. Okay, we will get an alkene also, because here a double bond is being formed. It will look like this. CH2, yes, and we will get a NaBr also. So here elimination takes place because we are eliminating one hydrogen. So elimination competes over substitution. So it would be substitution. It would be if it would have direct attack on carbon, but due to steric reason, since it has steric reason from this and this group, therefore this attack cannot be facilitated and deprotonation was preferred. and we got this thing. Clear? So this is our elimination reaction. So this was the exception. Now I have told that if we have time, then we would cover this thing, that is from alcohol, using a different method other than dehydration. So if what we do for that, we take alcohol. Okay, we take alcohol, and rather than acid, we take a base. Suppose we took a base, that is pyridine, and we take 2 moles of it. Then in that case, you will see that you got ether. Now, what is the reason behind it? So how this mechanism goes? So it goes in this way. So you have our CH3OH. Yes. And the structure of pyridine looks like this. Yes, the structure of pyridine. Now this pyridine is a base. It has a lone pair. So what does it do? Take a H. Now some of you would say, so it is just for your curiosity, that this lone pair must be delocalized above the benzene since it is aromatic ring, but it is not so. It will never be so, because since it is a aromatic system, therefore according to Huckel rule, it should have 4n plus 2 pi electron. If you include this thing also, it would result in 4n pi electron. So if you look at it, 1, 2, 3, 4, 5, 6, 7, 8, that is n is equals to 2, therefore 4n pi electron, then it will be anti-aromatic. Therefore, its lone pair are not delocalized over this ring. It is present on nitrogen. Now this lone pair takes your hydrogen, and we got CH3O minus. Now we will have another mole of your, say, CH3O minus. We have another mole of this CH3OH. Okay. Now what it will do? It will attack this thing. Okay. And it will be removed. Yes. Clear? Then again you will get your ether. So this mechanism is not very obvious because we have seen that we have a removal of OH group. Okay. So what you would do in the second step, you would just treat it with with acid. Clear? You can treat it with acid to facilitate your reaction. So this is the second method. Or in this place, you can treat it with the second step. So I would suggest a more better approach. If you take a Br here, then it would give this thing. Okay, so let me just modify this reaction. Sorry for this, because this OH group is not a good leaving group. Now this Br can leave. So it would result in CH3OCH. So if this question comes in exam, it would come like this. But we have CH3OH, any alcohol, we treated it with pyridine. Sorry. Pyridine would look like this. Yeah. It's called pyridine. We got your product A. Then the next step, we treat it with a alkyl halide. Here, we treat it with the alkyl halide. Then we got CH3OBr. Now this step is similar to your Williamson synthesis. So why I have mentioned this thing, because sometimes in exam you may not get this thing, that is your alkoxide directly, CH3O minus Na plus. Instead, you may be given a process to convert from alcohol to this thing, and for that you must be given a complicated base like this. So for that I would suggest that if you get a compound that is complicated, just try to draw the structure of it. Then it would be easier for you to understand that how it would function. So if you just thought of pyridine, if I would have just thought of the pyridine, then it would be difficult for me to consider the reaction. But since I have drawn the structure of this pyridine clearly, then I saw that okay, we have an acidic proton from alcohol and we have a basic nature from nitrogen lone pair. So it is a Lewis base. Since it is donating electrons, so it is a Lewis base. Okay, and we got this alkoxide. Clear? So this is the reaction. Now, what we have studied so far in today's class. So we have started from the nomenclature, in which we said that if you look at a structure of ether, then we would give the oxygen to that. We will name it in this way, that we will name each of these separately, and how the each of these group will be named separately. The oxygen will go to that alkyl group which is shorter in length. Now it becomes a substituent. Suppose it is methoxy, it becomes a substituent. Now we see the longer chain. So we will name it separately 1, 2, 3, or 1, 2, 3, 4, 5, anything. We'll name it in that way such that the oxygen groups comes faster or in the higher priority. So we will first keep the name of this. Suppose it is methoxy, then methoxy, whatever with the number n methoxy. N means the number, the priority it is getting. Suppose it is 3 methoxy or it can be 4 methoxy. Then if it is a further substituent, you can keep that also. It has methyl, 2 methyl or 2 ethyl. Okay. Then the alkane base name. Suppose it is butane, we'll name it as butane or hexane, anything. Yeah. Now one common rule for the nomenclature should be followed here also, that while writing the substituent, you must follow the alphabetic order. Similarly, if you are writing the common name, you will again follow the alphabetic order. You will name the both of the substituents on each side, say independently. Suppose it third butyl on first side and isopropyl on second side, then it will be third butyl isopropyl. Now to decide the order of this, whether the third butyl is written first or isobutyl, just follow the alphabetic order. So since I comes first, we will write isobutyl, isopropyl, third butyl, and the ether word. This is the common name. This would be the common name. Then we have seen the methods of preparation of each of these. The first of these ethers, the first one was your from dehydration of alcohol. Okay, so in dehydration of alcohol, we have seen that it has a drawback, that we cannot use it to prepare alkyl halide which has an ether which has a degree greater than 1. So we can use only to prepare primary ether. So we take alcohol, we treat it with acid at a lower temperature, or you can say specific temperature, so that alkene cannot be formed. In the second, we can form this tertiary ether, but tertiary can be on one side only. Tertiary carbon can be on one side only, it cannot be on the other side. So for that, we use the Williamson synthesis. And the alkoxide that we took can be primary, secondary, tertiary, anything. But the alkyl halide can be only primary, because if it not had been primary, then it would result in elimination reaction and the formation of alkene. Clear? So basically, the alkoxide attacks our alkyl halide group, the alkyl halide leaves, and we got our ether. So, and at last, I have told you that there is a method of preparation of alkoxide. So you can be asked in that way also. So you should be prepared that how to tackle that problem. Okay. So this was for today's lecture. Tomorrow we will be seeing the chemical reactivity of the ether. Also, one more important thing we studied today, that why this ether is least reactive. So it was basically due to the less polarity, because the same atom was present on both sides of the carbon, that decreases the polarity of ether as compared to any other functional group. Clear? So due to this, we have less reactivity of ether. We will look at it, that how this reactivity goes tomorrow. Also, we will look at some of the commercial uses of alcohols and phenols. Okay. So this was for today's class. With this, I would end my lecture.